Alright, draft science video, physics number 7 I think. Kind of disappointing results here, no new comments at all the last two videos. Nothing. So, that's got to do better than that. So anyway, thought I'd go over, I've been watching some different videos on this, I should be doing the magnetism thing, but I'll get there. So I've been doing the relativity thing, special relativity, and this whole idea of time travel. It really isn't time travel, and they all the talkers on this subject, they always say the clocks aren't changing, yet they're conceding that the matter of the persons are changing, which is kind of, if the matter of the person's changing, then why wouldn't you think the clock could change? Well, anyway, so we're back to this metabolism argument, the metabolism of matter, and that's all that's really happening, is that you're just slowing. You're not slowing time down. You're slowing the function of your matter down. The time around you is still going at the right speed, but because you're moving, you're changing. And they don't even talk about, like, these thought experiments really have so little value. So they don't even talk about the obvious changes, that if you ever accelerated a human body to 80% of the speed of light or anything close to that, but even accelerated them, a few thousand miles an hour, 20,000 miles, 30,000 miles an hour, just the forces of the acceleration to get up to those speeds, you'd have to accelerate very, very slowly. And just because you can just imagine, it's like being in a centrifuge, right? I mean, you're basically putting to get up anything at real speed, you'd have to put a body in a centrifuge and spin it. And essentially, you could understand how, all the heavy parts of your body would start to be pushed to one end of your body, and that's the same as acceleration. So anyway, this whole thing comes about because of this not a real problem of understanding what movement is, and even the lack of concession that all you're really changing is the frequency of light. Say if you're moving, so you can do this idea of two things, stationary, and then some photons are coming at it, the two things, and if one of these things is moving, that somehow this thing becomes faster because this thing's moving, so you have to multiply the speeds. You have to add the speed of this to the speed of that, and because they somehow combine. And they realistically don't combine, especially when you understand that these things are discrete things. These are photons with a frequency. So as you speed up, you don't make these things go any faster. You just make their occurrence happen more often. So the speed of whatever's coming at you in terms of a photon or light would remain the same, but the frequency would be, the frequency of the hits would be, you would hit the hits more rapidly as you were moving through them. So your speed would change the frequency, and that's basically what's called redshift. You're just changing, you're encountering the photons more often. The interesting question would be if you could redshift sufficiently to change to change light into, say, a microwave, or to change it into another form of electromagnetic energy by just encountering it quicker. That would be an interesting question, is how much you can shift. Redshift something. Can you redshift it into another form? Or, for that matter, blue shift by going, running away from it fast enough. But these frequencies are very high, and obviously to make a substantial change in frequencies that high, you'd have to go very fast. More interesting would be radio waves. They have a longer, slower frequency, and I don't know whether any real work has been done into moving into radio waves and you know, changing them into, yeah, I guess it would be microwaves after radio waves. Anyway, you know, this has always been kind of curious. This question of whether these single photon, the idea of a single photon, whether it automatically is some sort of paired item. Like we call it a single photon, but it really does carry frequency information, in that it has a distinct you know, portion of middle, you know, separating it so that each photon would carry a frequency signature. Because otherwise the photons could just be always the same substance, just changing the separation. So an X-ray and you know, a photon of light could be the same photon, just changed in frequency. Is that a possibility? You know, you get into light polarization, all these other issues that come up in trying to think about that. So, but anyway, so that's a part. I haven't gone through all of this stuff, but I mean, the part that I want to get to is just this idea that what is, you know, fundamentally what they're not realizing here is that these are discrete particles. Whether they're discrete in the sense that they're a little machine themselves, they're still a discrete mechanism, you know, an individual mechanism. And the constant is the speed of light, and the speed of light relative to the speed of light. And so back to, you know, you have to think of think of it this way. You know, even if there were a capacity to move in different directions, just to imagine that there's really only 4 directions. Okay, there's, you know, left, right, forward, back, up, down. And so that would say that you'd have 15% of movement would be in any one of those directions. Obviously it could be in some mixture of them, but I'm just saying as a way of understanding it, that when something's stationary, it's that every direction has 15% of its pressure. So 15% of your matter is moving one way or another way or another way or another way when you're stationary. You know, but we're not, obviously right now we're moving because we're on the earth and all this other stuff, so we already have a change in that dynamic in some percentages. And when you're moving, you know, fast, what has to happen is that one of these directions is going to get a higher percentage, you know, say 30% of the mass has to be going in that direction for you to achieve that directionality. So if you had like 100 pieces, you know, 30 of them would have to be, generally speaking, going in the direction you're going. So again, back to the school of fish argument. So if you have a single photon moving at a regular rate of the speed of light, you know, c, and it's coming at, you know, you're going to encounter it. What's really the matter you're made out of is really matter where some bits of it are, they're doing the same thing as this stuff is doing. They're moving exactly at the same speed this stuff is moving at, except some pieces are moving in this direction and some pieces are going that direction on every, say, clock tick. So this would be one clock tick of time, one clock tick of time, one clock tick of time. One clock tick of time, portions of this stuff is moving in different directions with a net effect of having extra movement in this direction. So more of them moved in this direction than moved in any of these other directions, is all you're really saying, to create movement in a direction. What did I want to get to? There was some more important feature of this. So yeah, it's again, so again, to understand what's happening when matter is moving, you know, they talked. I saw one professor talking about how they have some sort of thing at the end of the universe that's moving 80% the speed of light, a galaxy or something. I have to look that up. I guess because it's so redshifted. I would think with that much redshift, it would sort of have an answer to my question about whether the redshift changes the light into something else. But that's something to check out. But it doesn't sound right to me. Just because 80% of the speed of light, you're saying that 80% of, you know, the structure has to be moving in this direction. And, you know, it's possible, but not with normal atoms, I don't think it is. But anyway, the point is what's really happening in the orbits of the atoms to understand when you're moving something. So I'm going to make it geometric instead of making it round orbits, just for the sake of simplicity. But you have to just kind of understand that idea of it. It's moving less distance this way and more distance this way. So it's, you know, it's a mechanism of circularity. So it could just be something as geometric as a square, and this is the way it normally moves. And it could be held in that condition, you know, by some other mechanism, you know, that is just the same idea. So these would be the parts of atoms, would be the things that are holding them together would be that they're not really being held together, they're just trapped or interlocked in between each other, or they're interlocked by some mechanism that allows for this movement here at a certain speed, recognizing that that speed has to be slow enough to allow, say if you tied a circle like a lasso to a single point, and so this is spinning, this lasso is spinning. The question is, how much spin would you have to have in this rope to be able to get it to go to a single point? And where that single point could still, you know, spin or rotate at the speed of light in this small density of space, and still have these things moving at the speed of light and have the same orbital or something close to some kind of similar. So in a sense, this orbit, each orbit would have this spiral would pretty much be like this picture. It'd be like a cone that has to go out to hold that orbit in place, and each orbit has to get smaller and smaller and smaller. But it also has to, you know, it could wobble, so you can get multiple frequencies into this thing. Well, I didn't want to get into the subject of what binds atoms together, but you know, I really wanted to do this movement thing. So the idea to understand is that there would be the ideal condition is some sort of, you know, perfectly neutral, perfectly centric. Every piece is centralized. Every piece is comfortable. But the uncomfortable position of movement creates an obligation to maintain this order. What has to basically happen is this direction has to be shortened, and this direction has to be lengthened. And so what's kind of happening is that the orbit is being changed in the sense that it's eating a little more space in the positive direction, and when it comes back, it keeps coming back less. So it goes out further and comes back less. It goes out further, comes back less. It goes out further, comes back less. It goes out further, comes back less, right? So it's doing this, you know, that's how it's moving in a direction. And changing this orbit would also have to drag whatever the connecting mechanism is, obviously would also have to be, in the same sense, reshaped to be able to drag along. So the whole mechanism has to be dragged. And so when you're talking about normal movements, you know, they're much slower than the speed of light. I mean, light is, you know, I mean, light travels, okay, so it's a foot in a billionth of a second. So in 1 billionth of a second, light travels a foot. Clearly this, okay, like 1 second per foot, is 1 billion times slower than the light is moving. So that's 1 billion times slower. So, and that was probably 40 miles an hour. Something like that. That movement there was probably, let's say, 30 miles an hour. I guess I should figure out how fast. Well, it doesn't really matter. So I'm just saying the speeds we're running at are very small percentages of the speed of light. So even if we were going 1,000,000 miles an hour, we're still 1,000 times slower than light, right? You know, 1,000,000 miles an hour is a lot of speed. So to understand, that's, you don't need much of an increase in the percentage of the material moving in a direction to acquire pretty fast speeds. So you could say that when you're going 1% of the speed of light, I should find out what 1% of the speed of light is, right? How many miles an hour is that? You know, that's pretty fast. Okay, so, but it's, you know, it's only 1%. So that would be the point I'm making, is that all you need is 1% of this eccentricity in a direction. You only need 1% of the total orbital change here. So 1%, a 1% change in an orbit is very small. I mean, if it was an ellipse, a 1% ellipse is almost, I mean, you could detect it, but it wouldn't be very dramatic. It wouldn't be very obvious, a 1% deviation in the circularity of a circle. But that's still a substantial amount of speed. So my argument is we don't commonly ever see anything moving very, very, very fast. Even a bullet is not going anywhere close to a significant speed in terms of the speed of light. It's still less than 1%, right? So it's incredibly slow, and you know, but obviously perceptually it's very fast from our perspective. So the speed we're talking about here, where you could do any of this time dilation stuff, are incredibly fast speeds, and I think it'd be rational to recognize that at those speeds the atomic structure would be changing, and that it seems quite logical to imagine that atomic clocks and everything else would be affected by these time changes, by these material changes to structure, because now they're being forced to do this eat more space thing in a direction. So they're being forced to change every orbit inside of all of the atoms, and that it's going to take longer. Again, the argument being made here, it's going to take longer to complete these cycles if you have to keep reorienting in a direction. The only way they can make up that reorientation is in the slowness. You're eating more space. So again, well, I said in the other video, it's like adding spaces to the Monopoly board. It just changes how fast the thing can rotate, because it's got to eat extra squares. All right. So yeah, it's a little bit too. I mean, I don't know how helpful this is in explaining things, but you know, the idea is that the fundamental argument of special relativity is that the clocks aren't being physically changed, that time is still being measured accurately. And no, I think the clear argument is that space isn't dilating, matter is changing. So when you move matter, you change the matter. The matter has to change to accommodate the movement. The interior parts have to change to accommodate the eating of the space. So again, we're back to this checkerboard thing, and that's really the way to understand it. From the perspective of the checkerboard, if there's something moving on these checkers this way, the other stuff, the matter, is also moving on the squares, and from its perspective there is no momentum. There's just bits that move in this direction and bits that move this way, and then this way, then this way, then this way. And they're obviously, if the distance is increased, if you're taking more steps, obviously if you take a zigzagged or you go a straight line, there's obviously more time to go the zigzag, and that's all that's really happening here. Is there's no change in real time. There's just change in how you're covering the distance between the two things. And there's the straight line way to cover the distance, and then there's the crooked line. And the matter, most of the matter, because it's moving much slower as a whole, the whole school of matter is moving much slower than the light. Most of the things in the school are obviously taking this jagged line. So distance is much greater. So you could argue that it's distance dilation because these subatomic particles have to move more distance to do the speed thing. To do the movement thing. Okay. So I think that, but obviously there would be no additive effect beyond the fact that, of course, in time you'll get to each other faster if you're both moving towards each other, and it would take longer. You know that obviously you're going to eat more space between you if you're both coming at each other. But each jump of each square is the same amount of energy, the same amount of momentum, the same. From the perspective of the quanta, there is no momentum here. There's just quanta moving squares. There's just photons moving squares. So there is no such thing as momentum. There's no such thing as movement, except the subatomic particles are moving the speed of light. So from the real universe's point of view, the real universe is your subatomic universe. That's the real universe. Okay, the real universe isn't space and you in space. The real universe starts at the subatomic level, at the photon level. That's where the real universe exists. And what you're experiencing is a much more confused, complex motion area where you have a bunch of stuff swirling, and you're not riding on the stuff swirling. You're not seeing the universe from its perspective, and it's the thing that's really interacting in the universe. You're not interacting. The photons, the pieces making you up, are interacting with the universe. Okay. Well, I hope to get to magnetism soon. Yeah, I just want to. All of this gets a little bit tricky when you start layering it, and you have to account for all these movements, and there are so many pieces. Even like I said, just imagining light, the volume of it, in just one blink of an eye, the massive number of photons that are impacting. It's just, so it just makes getting it right conceptually, recognizing what's happening. It gets tricky because there's so many fish, and sometimes the fish are caught in swirls of other fish, and and they're all the same color. Sometimes it's a little difficult sometimes to conceptually recognize, to stay with the fish and not get confused by the swirls of the schools. I think that's the way to put it. Okay, until next time, if somebody has some suggestions about who I should maybe contact, the academic thing just doesn't work because they want affiliations and all this other crap, and they're not going to deal with. I think this is better explained with diagrams, like a lecture, I think it's better to be able to explain it this way than to try to write it into something. So that's the other thing. Einstein's postulate on special relativity was not complex, and my postulate is not complex. It's there. It's just my postulate is matter is made out of photons still moving the speed of light, and you can't move any of those photons faster than the speed of light. So anything the matter does has to do it within the rules of not having any of the interior photons moving faster than the speed of light. It's a simple postulate. But anyway, okay. So I'm just well, whatever. I'll just keep working. I mean, it's only 2 weeks in. I shouldn't get too. I mean, I figured it would take a year. You know, but yeah, you just want it. You're just like, oh, this is so obvious. Somebody ought to just say, oh yeah, Gary, you're right. This is the way to go. Now let's let some real physicists work this all out. I mean, this is the right model. They have the wrong model. They don't. They just didn't recognize the fundamental truth that all of these effects are happening because the matter is not matter. Matter is energy, and it's energy still moving the speed of light. That accounts for everything. Okay. Till next time.